Welcome to the physics basement. Don't look out there. Don't look out there. Just stay down here. Stay down here and learn physics. That's what we should do. Ignore it. Like for the next whatever many minutes, let's just be chill. Let's talk about a physics problem. So, you have some charge Q, a distance d, above some infinite grounded conducting plane. Grounded means the potential across the plane is zero. But what is the potential above the plane? Like, there's a charge there. There's an electric field there because there's a charge there. There's some sort of electric potential there. Electric potential tells us how much work it will take to move some test charge through this field from one point to another. You could relate electric potential in electromagnetism to gravitational potential in mechanics and gravity. What we do know is that charge just being there, some distance d, above this infinite grounded conducting plane will induce a charge across this conductor. What we don't know is how much charge will be induced across this conductor and how that charge will be spread across this conductor. And that becomes a problem because the traditional way to answer the question, what is the potential above this infinite grounded conducting plane due to this charge, is to solve Poisson's equation. If you know the electric field, because you know the charge density distribution, you can calculate the potential field. If you know the potential field, you can work backwards and get the charge distribution. You can reveal Poisson's equations in electrostatics by starting with Gauss's law and setting the magnetic field to zero because we're doing electrostatics. And you get this equation. And it looks exactly like what I just said, right? If you have the charge distribution, you can get to the potential and you can work it back and forth. But we started this video asking what the potential was of this setup, and we don't know the charge distribution. And to use Poisson's equations, you have to know the charge distribution, and we just don't. We simply do not know. So how do you solve this problem? Well, the next thing you do on your little checklist of solving a physics problem is look at the boundary conditions. So at zero, z equals zero, where this infinite grounded conducting plane, we know the potential is zero because our plane is grounded. And then we can assume at infinity away from this charge, the potential is also zero. It has just fallen away. And in electrostatics, there's something called the uniqueness theorem, which says, okay, we have a boundary, and on that boundary, we know what the potential is. And inside the boundary, we also know the charge distribution. There is only one function. There is only one potential that could fit both those things. This video isn't about the uniqueness theorem, but you can look up a proof, but also it does feel like it makes sense. Like, you know what's happening at the ends, and you know what's causing that to happen. There is only one function that can make all of that true. There is one unique solution to that problem. And this realization, this idea that, hey, only one function could answer this question, leads to this trick, this neat little physics trick, this 10 out of 10. It's a good one. So let's take our problem with our point charge Q, some distance d above some infinite grounded conducting plane, and just shove it away and think about a totally different problem. Imagine you have one charge Q, a distance d away from the z equals zero plane. There's nothing there. It's just where our coordinate system is. And minus d, below it, you have a negative Q, an oppositely charged guy. For this system, we know exactly where all the charges are. Right? We have a Q and a minus Q. We know their positions. We can easily just write down the electric potential of this system of charges. Here it is. What this is telling us is the electric potential at any point x, y, and z, that's its coordinates, away from these charges. Looking at this, let's do the next thing you do when you're solving a physics problem, which is think about the boundary conditions. At z equals zero, when you plug in z equals zero to this equation, you get that the potential is zero. The next one, very far away, when r gets much, 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 much bigger than d, this also goes to zero. And in electrostatics, there's something called the uniqueness theorem that says that if we have this charge distribution and we have this list of boundary conditions, there's only one function that will satisfy this system. There's only one answer to this problem. Only one function will meet these requirements. Wait a second. So the potential in this problem is the same as the potential in this problem, and you can just use this in this problem to, get all the answers you need. You could use this potential to calculate how much charge develops on the infinite grounded conducting plane. And the answer is minus q, which if you think about it, of course that was the answer. But we're physicists, we have to check. That's why we check things. But also just think about it looking from like the field lines. You know what the field lines look like around like a dipole. Looks like this. Shove that q over here, you're going to get half a dipole. Of course, minus q develops on the plane. Of course it does. It has to. And of course, the uniqueness theorem says, hey, the potential here has to be the same as the potential here. Of course it does. It has to. However, there are some caveats. This minus q we invoke to solve this problem is an image. It's not an actual charge. This is a real setup you could deliver. Down here below this plane, there is no minus q charge. We used an image charge to solve the problem, but that charge doesn't exist. Placing a real charge above a real grounded conducting plane does not produce a real opposite negative charge any more than you going to the bathroom and staring in the mirror produces a real clone version of yourself some distance d behind the mirror. That's just an image. And because of that, while the potential in this region of these two problems is the same, everything's not the same. For example, the energy trapped in this field is going to be half the energy trapped in this field because this whole component doesn't exist. You know what I mean? But this trick is so good. It makes so much sense. It makes unsolvable problems solvable. That's bonkers. And what's wild to me is when you learn physics, when you read physics textbooks, this is presented as like, look at this tool. We could use the method of images instead of like, holy shit, look at this really cool math trick. The presentation I just did with the infinite grounded conducting plane is the one people do. It's in Griffiths, it's in Jackson. It's in James Jean's Theory of Electricity and Magnetism, a book from 1919, in an identical manner. Exactly the same presentation of this brilliant physics trick without celebration. And I think it needs to be celebrated. This is a great idea. You can just do this. Okay, so you're gonna have to bear with me for a second, but about a year ago, I saw this video with Cynthia Erivo, and she was ranking like what she considered the top best vocal performances. And the thing about Cynthia Erivo is like, obviously she's a very good singer, she's very talented, but also she studies music. Like that's her field of study. She's an expert in theory as well as like very good at using her instrument. And so when she's watching these very good technical performances, she's making this face of like, she sees Aretha Franklin sitting down at a piano, just absolutely belting. And she's like, that's rude.
It's so unnecessary.
And I feel like that's very common. Like someone who's really good at the bass will hear a really good bass riff and they'll call it nasty. Do you know what I mean? Complimentary, of course. And now that you are an expert, you understand how hard this problem would be if we didn't use the method of images. So when you look at the method of images, I hope you're with me when I say, that's nasty. That's rude. Are you kidding? You can just do that?
Come on! So rude. It's so crazy. It's so rude. It makes me want to swear. Why are you doing that?
The thing you always need to remember about studying advanced physics and solving advanced physics problems from textbooks is, of course, that the problems that are in textbooks because they are the problems we can do. Electromagnetism in the world is much more difficult because the world, exists. The world is physical. There is no such thing as an infinite grounded plane in real life. You can approximate it. There is no such thing as like a perfect stationary charge. There is no such thing, like what's the medium that this electric field is traveling through? All of those things will affect like whatever you're setting up. So do you think a professional experimental physicist ever sits down to like use the method of images? When would it ever be actually applicable to real life? And the answer to that is like, yeah, they do. Of course they do. While a real physical experimental physics setup is going to be much more complicated than anything you'd ever see in a textbook. Like try setting up a waveguide in real life. Okay, what Well, you can use things like this for, like, how much shielding would you need? Well, you could set up like an example, simple version of the problem with your method of images and solve it real quick and get like the maximum and minimum amount of shielding you would need and just use that as a baseline, and then you would test your experiment to make sure that that worked. You would use it. Why doesn't anyone ever talk about how bonkers this trick is? It's really good. It's a good trick. It's disgusting. It's rude. How dare they? So where did this come from? Who came up with this trick? Where does the credit belong? In some textbooks, especially much older textbooks, this was called Kelvin's method of images, because this is a Lord Kelvin joint. That's why he's a lord and you're not. Just kidding, but like put a pin in that. Lord Kelvin, before he was Lord Kelvin, discovered this mathematical physics text that was written by Green of Green's functions. I feel like his name is George Green. Look that up, Angela. Make sure it's George Green. Anyway, inside of it, he saw that George Green had previously, I really hope his name's George now, had previously worked out like a lot of the work of Poisson. And looking at it, Kelvin kind of got inspired with this idea of the method of images. And of course it follows through today because it's really useful and really helpful. And it's a really cool trick.
It's so unnecessary. Why do you need to sing that? So much. And he just keeps going. Why? It's so ridiculous. What? I'm undone. I can't deal with it. I'm sorry. Come on! So rude. It's so crazy. It's so rude. It makes me want to swear. Why are you doing that?
The reason Lord Kelvin is because of politics. So like pour one out for all those people who are like, science isn't political. It could never be political. Like the reason the Lord Kelvin is so famous is because he became a lord. He was the first scientist to become a lord in the House of Lords. And the reason was because Lord Kelvin was from Ulster, even though he spent most of his life in Glasgow. And as he aged and he started getting some real kooky science ideas, he also became very political. And he was very, very against the home governance movement in Ireland. And he was like, guys, if Ireland left the UK, it might be bad for the UK. And like, we shouldn't do that. And the British government was like, dude, that is an idea that we should capitalize on. And they made him a lord. And they were like, see, Irish people don't want to be free. Look at Lord Kelvin. So, yeah.